Now I want to expand my ideas for changing variables to triple integrals. When I want to transform a function for triple integrals, the only difference between what we did before and what we need to do now is that my transformation function will now have three components. My transformation will be such that x is equal to g of UVW, y is equal to h of UVW, and z is equal to p of UVW. This transformation maps a region of S in UVW space to a region D in XYZ space point by point. The triple integral over the region D of f of xyz dA under the transformation becomes a new integral over the region S that will be easier to evaluate. But we do still need a Jacobian to make the transformation work. So if I'm given a transformation T such that x is equal to g of UVW, y is equal to h of UVW, and z is equal to p of UVW, where g, h, and p are differentiable on a region of UVW space, the Jacobian determinant, or the Jacobian, of T will be given by j of UVW is the partial of x, y, and z with respect to uv and w, which is found by computing a determinant of a 3 by 3 matrix, where the first row is populated by the partial of x with respect to u, the partial of x with respect to v, and the partial of x with respect to w. The second row is populated by the partial of y with respect to u, the partial of y with respect to v, and the partial of y with respect to w. And the third row is populated by the partial of z with respect to u, the partial of z with respect to v, and the partial of z with respect to w. Now, you might recall that computing the determinant of a 3 by 3 matrix can be achieved by expanding about the first row, and I get the element a sub 1, 1 times the element a sub 2, 2 times a sub 3, 3 minus a sub 2, 3, a sub 3, 2 minus the element a sub 1, 2 times a sub 2, 1 times a sub 3, 3 minus a sub 2, 3 times a sub 3, 1 minus the a sub 1, 3 element times a sub 2, 1 times a sub 3, 2 minus a sub 2, 2, a sub 3, 1. This is the method of minors and cofactors, expanding about the first row. But if all of your elements are numeric, just use your calculator here, or I find it simpler to use the method of diagonals. Let's work an example. I want to evaluate the Jacobian j of UVW if I'm given x is equal to u plus 2v minus w, y is equal to u minus v plus 2w, and z is equal to minus 2u plus v plus w. My partial of x with respect to u is 1. The partial of x with respect to v is 2. The partial of x with respect to w is negative 1. The partial of y with respect to u is 1. The partial of y with respect to v is negative 1. The partial of y with respect to w is 2. The partial of z with respect to u is negative 2. The partial of z with respect to v is 1. And the partial of z with respect to w is 1. The Jacobian is the determinant of a matrix populated by 1, 2, negative 1 in row 1, 1, negative 1, 2 in row 2, and negative 2, 1, 1 in row 3. The method of minors and cofactors gives me 1 times the sum of negative 1 and negative 2, minus 2 times the sum of 1 plus 4, minus 1 times the sum of 1 minus 2, which is equal to negative 3 minus 10 plus 1, or negative 12. This is very easy to do in your calculator. The absolute value of my Jacobian is positive 12. So if I let t be defined by the transformation functions x is equal to g of UVW, y is equal to h of UVW, and z is equal to p of UVW, and this is a transformation that maps a closed bounded region S in UVW space to a region D is equal to T of S in XYZ space, and if we assume that T is 1-to-1 on the interior of S and that G, H, and P have continuous first partial derivatives there, then if F is continuous on D, the triple integral over the region D of f of xyz dA is equal to the triple integral over S of f of g of u v w, h of u v w, p of u v w, times the absolute value of the Jacobian of u v w, dv. Let's work an example. I want to use a change of variables to evaluate the given integral. I'm looking to evaluate the triple integral over the region D of dv, where D is bounded by the upper half of the ellipsoid, x squared over 9 plus y squared over 4 is equal to 1, and the xy plane. I want to use the transformation functions x is equal to 3u, y is equal to 2v, and z is equal to w. My Jacobian of UVW is given by the determinant of a 3 by 3 matrix, where the first row is populated with 3, 0, 0, the second row is 0, 2, 0, and the third row is 0, 0, 1. This determinant is equal to 6. This will give me a triple integral over S of 6 du, dv, dw. Our new region is bounded by u squared plus v squared plus w squared is equal to 1, and the UV plane. This is the upper half of a sphere with a radius of 1. We could complete the integration process here, or we could choose to work smarter rather than harder. We know the formula for the volume of a sphere is given by v is equal to 4/3 pi r cubed. So if I take half of that volume and multiply it times my Jacobian, I'm going to get an integral value of 1/2 times 4/3 pi times 1 cubed times 6, which is equal to 4 pi. So now you get to try it. Pause the video and evaluate the given integral using a change of variables. When you're ready, restart the video to check your understanding. You want to evaluate the triple integral over d of dv, where d is bounded by the planes y minus 2x is equal to 0, y minus 2x is equal to 1, z minus 3y is equal to 0, z minus 3y is equal to 1, z minus 4x is equal to 0, and z minus 4x is equal to 3. In order to evaluate this integral, I'm going to look at my boundary lines for my region. I'll note that if I let u equal y minus 2x, v equals z minus 3y, and w equals z minus 4x, we can solve for x, y, and z in terms of u, v, and w. X will become negative 3/2 u minus 1/2 v plus 1/2 w. Y will become negative 2u minus v plus w, and z will become negative 6u minus 2v plus 3w. My Jacobian will be the determinant of a 3 by 3 matrix where the first row is populated by negative 3/2, negative 1/2, and 1/2. The second row is populated by negative 2, negative 1, and 1, and the third row is populated by negative 6, negative 2, and 3. This determinant gives me 1/2 for my Jacobian. Now my integral becomes a triple integral over S of 1/2 du, dv, dw. My new limits of integration are from 0 to 1 in u, 0 to 1 in v, and 0 to 3 in w. This means that my triple integral will become the integral from 0 to 3, of the integral from 0 to 1, of the integral from 0 to 1, of 1/2 du, dv, dw. Working from the inside out, I get the integral from 0 to 3 of the integral from 0 to 1 of 1/2 dv dw, which gives me the integral from 0 to 3 of 1/2 dw, which is equal to 3/2. This is how I can go about changing variables with triple integrals. Be sure and let me know if you have any questions.